First, we have Pavel. And one thing that I'd like to say before we get started is that this is going to be a meetup that's going to be geared towards people who are looking to get into audio software development. So if you're just getting started, or even if you haven't started yet and you're looking to get started, I think this is a great meetup for you because we're going to discuss two of the most common questions that we get in the audio programmer community, one of which is, what are some of the basic fundamentals that we need to know if we wanted to be audio developers? And Pavel is going to talk about that. And then normally the second question that comes right after that is, well, how do I get a job in the industry? What do I need to do? What skills do I need to know in order to get a job at a company like Ableton? And we've talked about those sort of things a couple times, but I think it's just great to hear different people's experiences. And so we have Jose, and we're going to discuss that and more. Jose has just been newly hired by Ableton, so he's only been there for a couple weeks now, and I think it'll be great to get a fresh experience from somebody who has just kind of made it in the industry and just getting started and the steps that he needed to take to get there. So let's go ahead and get started, and we'll start with Pavel. And Pavel got an engineering degree in missilery from BMSTU. He loves C++ and knows how to cook it. He likes metaprogramming, multithreading, and asynchronous programming, and is a coroutine adoption enthusiast. So he knows his C++. And today he's going to speak to us about building intuition for sample rate and aliasing. Take it away, Pavel.
Yes, thank you. Let me share my screen.
And as he's sharing his screen, one thing that would be great is if you have any questions in the chat, please precede those with question in all caps so I can see them easily and I'll be able to ask Pavel. And we're also going to be asking these questions during the chat as well. So if you have questions about what he's actively discussing, please ask, and then we will ask him pretty much right on the spot. Over to you, Pavel.
Yes, thank you. Sorry for showing my ceiling and for weird camera angle and for not looking at the camera, but I need to operate my computer in order to tell you about all this. And we'll try to build intuition for sample rate and aliasing. First of all, first of all, disclaimer, I'm a programmer and I will talk about audio basically, but I'm not audio programmer. And please, Josh, post this link to chat. Please go to this link, go nuts with the toys. You maybe want to leave me in the background and listen to me in the background while you are playing with the toys. And when you are done, you probably may come back and listen to some explanation about it. So anyway, go nuts with it, please. And let me go to this page. This is basically the page that you have the link to by now. And we'll talk about sample rate, first of all, and we'll try to internalize and get intuition for the phenomena called aliasing. So sample rate is somewhat straightforward. So when we want to convert analog continuous signal to digital signal, we want probably to measure the signal from time to time. And these measurements or sampling will give us some values or samples, so-called samples. And here for this continuous signal, the blue line, which evolves along the horizontal axis, we measure it from time to time, and we get values which are represented by these circles, which get some position in the horizontal axis, which corresponds to the value of the sample. So when we're sampling, we can sample at some irregular intervals, but it helps a lot to analyze and process the digitized signal when we sample at regular steady intervals. When we do that, we can talk about sample rate. So sample rate is the rate at which we measure the signal, in other words, sampling the signal. And sample rate is measured in hertz. So it's like some number of times per second. And we can play with this demo a little bit, and we can see that when the signal changes, our measurement and corresponding samples are changed as well. So, okay, now that we got samples, if we want to just get samples and do some digital processing with it or some analysis, we can stop right there. But oftentimes, we want to get that some processed digital signal back to analog signal, to continuous signal. For example, when we play audio back from our digital players, we have to convert that digital samples into like electrical signals and then to pressure waves, air pressure waves. So having the samples, what should we do to convert that signal, that digital signal, into analog signal? Do we use just horizontal straight lines? Do we use segments connecting the samples, or do we use like some strange shape? To address this, we have a theory called Whitaker, Nyquist, Katelynikov, Shannon sampling theorem. This is of 4 people. That's how much people discovered and rediscovered this theory. And I think that to understand that this theory, first to look at so-called Fourier series will help us. So here we have our initial function, initial signal, which is a step. It has discontinuity here. So here the signal changes instantaneously. But anyway, we can work with it, and we can represent this signal with a sum of some signs. So here is one sign that approximates this signal, and we can add some more signs in the sum to approximate better and better this signal. Eventually, it gets somewhat close, I'd say, but it will never get close, or rather, I'd say that theoretically, it will get exactly to the shape of the initial signal, but with the sum of infinite number of signs. And in practice, this is impossible because we can't sum infinite number of signs. And this step function, we cannot represent this step function with signs in practice. And but we can represent it with some order of like closeness approximation. And here you can see this approximation with the 10,000 signs, with the sum of 10,000 signs. It gets pretty close, but nevertheless, it's not exactly. It doesn't represent exactly the initial signal. So what we can do with this is actually we can like work it backwards in the reverse direction, and we can filter unwanted high frequencies of this signal. And when we limit our frequencies, our allowed frequencies to say 37 first frequencies, we get this signal. This is the filtered representation of this initial step function, step signal. And so eventually what the Nyquist-Shannon theorem says is that you can reconstruct the samples exactly if the initial signal is band limited and we pass this reconstructed signal through low pass filter. Low pass filter means that we pass all the low frequencies and filter out all the high frequencies. So basically here, if we come back to this, we can say that all we need to do is just use any shape and then to reconstruct the signal and then pass this signal through a low pass filter, and we will reconstruct the initial signal exactly. If our initial signal satisfies all the constraints, namely it is band limited. So I hope it makes sense for you. Let's look at another example. So here we have our initial signal is sine wave, and we get some samples evenly spaced, and we can with this slider change the frequency of our initial signal, and we see that our samples change with the initial signal, and nevertheless we can reconstruct almost perfectly the initial signal from that samples. So the initial signal is blue, and the reconstructed signal is orange. We can look at another example here. So here is the initial signal is the square wave. You may have heard about that, which is used very widely in audio production and not only audio production. And we can see that when we sample our step or rather square wave in some way, we get samples, and after reconstruction we get this approximation basically of this square wave. And because this square wave has a discontinuity, we can't represent it with limited bandwidth, with limited frequencies. And yeah, I should have added that this is not possible in practice because you can see, you can look at this in two ways. One way is that we need an infinite sum of an infinite sines with like smaller and smaller frequencies and amplitudes, or since this change is instantaneous, we need like at some point we need a term, a summand in this sum with infinite frequency to represent this instantaneous change. And in practice, neither of this is possible, so we get reconstruction like this. So we get like some wavy approximation of the square wave. And when you, for example, choose in your synthesizer wave shape which is square, you have to understand that what you get eventually is this wavy approximation. Okay, let's go to sine wave. Maybe we have questions. Please interrupt me and jump in at any moment.
No questions so far. Seems pretty clear explanation, but if anybody has any questions, please let us know in the chat.
Okay, I like to joke that either everything is clear or nothing is clear.
That's right.
Okay. So when we increase the frequency of the initial signal, at some point we get less than perfect approximation. So I hope, yes, you can see that it starts to break down. This happens because the floating point that is used is not perfect. It's forgot the word. Okay, never mind. It's not perfect. We can't perfectly calculate with that. And my algorithm that reconstructs the signal is also not perfect. I cheated a little bit. So, okay, what happens when we increase our frequency even further? And here we see that we are at the so-called Nyquist frequency. Nyquist frequency is, by definition, half of the sampling frequency. So if our sampling frequency is like 48 kilohertz, our Nyquist frequency is 24 kilohertz, half of the sampling frequency. And here we can see that we have exactly 2 samples per period. So this is a period, we have 2 samples, and for every period we have 2 samples. And we are unlucky here, in fact, because all our samples have fallen to 0 value, and we get just a straight line after reconstruction. So here, this is the point where we are at Nyquist frequency. If we go back a little bit, it starts to get better. But if we go past the Nyquist frequency, look what happens. As we increase the frequency of the initial signal, the frequency of the reconstructed signal decreases. So you see that there are more and more like periods filled within this space, but there are less and less periods of the reconstructed signal that we reconstruct from our samples. And basically, this is aliasing. So after we pass the Nyquist frequency, our when the frequency of the initial signal increases, the frequency of the reconstructed signal decreases, and at some point we get unlucky again, and all our samples get to 0 again, because it so happened that we sample at points where our initial signal crosses the 0 line. And after that, if we go even further, as the frequency of the initial signal, which is blue, still increases, this frequency of the reconstructed signal decreases as well. So this is still a aliasing, and everything that's above Nyquist frequency gives us aliasing. And this happens infinitely as the initial frequency increases. The frequency of the reconstructed signal increases up to Nyquist frequency, then decreases up to down to 0, and then again increases up to Nyquist frequency, and so on and so forth. Okay, let's look at a practical example. So here we have, okay, I forgot to excuse me, I forgot to turn on the sound.
That's okay. Take your time. Well, while he's doing that, just wanted to remind you for for continuing the discussion, please join our audio programming community on Discord. So it's a great place to connect with other audio developers, and you can join us on theaudioprogrammer.com/community.
Okay, let's try again. Can you hear it?
No, unfortunately not.
Okay. You can't hear it, right?
No, can't.
Okay, this is my fault.
It's okay.
What should I do? Should I reload the browser?
Yeah, give that a try. Here we go. And I will paste the link in again for people who are looking to follow along. So even if we aren't able to get this working, you will still be able to listen in the browser.
Yeah, you can totally go to this page and experiment it yourself. Strange. Okay, never mind.
Yeah.
Okay, let's try.
No luck, unfortunately.
Okay, maybe my microphone will pick it up. Oh no, we will have echo.
Yeah.
Okay, so
I think if you just describe what it was.
Okay, the idea was that when we play a sine signal that is like changes frequencies, we can see that there is. Can you hear it?
No, unfortunately not.
Okay, never mind. Oh, I know what to do.
Okay. Yeah, we hear something. That's a bit loud. Yeah.
Okay. I didn't want to torture you with high frequency sounds. Let's try.
That sounds great.
Okay, I can hear it.
Yeah, for people who are listening in your headphones, you may want to just turn this down a little bit. We don't want to break your ears. So
the idea here is that we can reproduce sine wave. Like the initial signal is the sine wave, but I will stop it. Most of the most interesting, I'm sorry for that phrasing, effects are nonlinear, and nonlinear effects can add frequencies. And well, I'll try to. Can you hear that?
Yep, all good.
Okay, so this is distorted sound. This is undistorted sound. Let me just. I hope you can hear it and you hear the difference. Otherwise, okay, you can experiment it yourself. What happens with when we have distortion is that we have additional high frequencies, high harmonics. So for this signal, we have like second, third, fourth, and some like high order harmonics. And when we increase the frequency of the initial signal, we see that the frequency of the harmonics increases also as well. So this is a linear scale, not logarithmic, that you might be used to. And we can see that after the highest harmonic bumps into the Nyquist frequency, it starts to go back. And the same happens with the other harmonics. They bump into the Nyquist frequency and start to go back. And this happens. So here, the highest harmonic was reflected from the Nyquist frequency, went all the way to the zero frequency ODC. And when we increase the frequency, it starts to go back. So this is basically the same process that we saw earlier. Okay, now what we can do about it? We don't want like this mess when we use intensively nonlinear effects on our signals. We can use oversampling. So let me try to play an example. Okay, I hope you heard that. This is with distortion. And you can see how all the high harmonics bounce back and forth between 0 and Nyquist frequency. Nyquist frequency in this case is 8 kilohertz, since our sample rate is 16 kilohertz. And this is the undistorted signal. So you can see it like a little bit clearer, like a little bit crispier. And this is the distorted sound. And all like different effects happen. And I'd say that sometimes, and most of the times, these bouncing effects like rising and falling tones are unwanted when we process our signal. So what we can do, we can use oversampling. So here we upsample our initial signal twice. So our upsampled Nyquist frequency becomes 16 kilohertz compared to 80 kilohertz of the initial signal. And we can see that the bouncing reduced by 2 times. So we have like more frequency space to accommodate for all this crazy aliasing of high harmonics. Okay, next we can do is filter our upsampled signal. So we keep only the lowest frequencies and filter out the highest frequencies that we don't need actually. Because after downsampling back to the initial sample rate, we will not be able to reproduce those frequencies anyway. So now we can see that if we just leave a little bit more frequency data, we can see that bouncing have been reduced significantly. And we can try to play. Honestly, I can hear a little bit of the aliasing, and what we can do is we can use oversampling with higher frequency basically. So we oversample 4 times, and our Nyquist frequency was 8 kilohertz, and sample rate 16 kilohertz, and we multiply everything by 4. And now we have Nyquist frequency 32 kilohertz, and this is the original non-filtered processed with distortion signal. And we can see that bouncing happens primarily at high frequencies, and only one. We are unhappy that we have only one, the highest frequency, the highest harmonic, bouncing back to basically 0. Okay, we can again filter this, and now we can leave only the lowest quarter, like contents, frequency contents. And what we can back is, I'd say much better, because bouncing was reduced compared to 2x oversampling. And we can, I'll try to play it again. So yeah, we can hear it a bit, but I hope you get the idea. So you have to play with the cutoff frequency when you filter the oversampled signal. And in practice, you will use up to 16x oversampling. And probably you will use 48 kilohertz for your initial signal, or even higher. And so we can see that for 48 kilohertz, all the unwanted aliasing happens at really high frequencies, and we can filter it out like this. So all the unwanted aliasing happens in the frequency space that we filter out, and we get somewhat cleared from aliasing effects signal back. And basically that's it, I think. Please ask questions. I will be happy to expand on anything you maybe didn't catch.
Yeah, I think that either everybody understands what you're saying or nobody understands what you're saying. But I think these visualizations, there have been a lot of positive comments about the visualization and how great it is, essentially. Yeah, so really nice. And I think I have a question maybe to kick things off if nobody else has questions. So what inspired you to look into this and to start looking into audio? Was it just curiosity or?
Yes, it was curiosity. I'm I think I'm curious like by nature, and I like to figure out how stuff works. And I was enthusiastic about audio for a long time. And some time ago, I watched a YouTube video about this topic, and it clicked for me. And but like you cannot play with this demonstration in the video, so I decided to make interactive toys.
Yeah, that's great. And tell us about your job now. What do you do? So what you're doing now doesn't have anything to do with audio.
It has nothing to do with signal processing in my like immediate job. So I don't know. Is this relevant somehow?
Yeah, very interesting. Yeah, I don't know if we have any questions. Just a lot of positive comments just about the visualization and how that was done. So what did you write that in JavaScript, or how did you do
that? Thanks for this question. I'd like to geek out about that. I wrote it in JavaScript and HTML and CSS as usual, and also I needed an FFT library to perform like signal to frequency domain and back transformation. And it happens that I didn't find JavaScript library that satisfies my needs and that is fast enough. And while programming that, I had to get familiar with EM scripting and WebAssembly and all that stuff.
Wow, amazing.
It was a lot of fun.
Yeah, sounds like it. How long did it take you to do it?
I think like a couple of months, free time.
Yeah, very nice.
Yeah, now I have to finish the text. It turned out to be the hardest part.
Yeah. And what does Align technology do? Somebody Googled it and said it looks like it's a medical technology company. Is that right?
Yes. Yeah, that's right. Yes, correct.
So
I'd say the primary product is Invisalign system that how do you say it? orthodontic system that like moves your teeth and corrects your bite and teeth position.
Yeah.
Yeah, we the team I'm working in works on the application for doctors.
Wow.
So doctors can interface with that development like system.
That's great. We have another question. Do you have any library recommendations for building blocks for frequency domain processing, like FFT, STFT? Any library recommendations? Sounds like you were pretty dissatisfied with what was out there.
Yeah, I found FFT.js library. It was like pretty fast, honestly, but it had no inverse transform for real data. So you had to inverse transform the whole spectrum data and then like get rid of the imaginary part, and that was like roughly twice as slow if you don't take into account that you have real data input.
I see.
And,
have you done any in C++ before? Have you done FFT with C++?
yes, and I took like infamous, like not infamous, widely known in narrow circles library called KissFFT, which is written in C, and it is really easily used and can be integrated into your application. So it was after I figured out the WebAssembly stuff, it was like almost trivial to integrate it into the web page.
What was it called again?
KISS, KISSFFT.
KISS FFT. I haven't heard about that one. That's interesting. Okay. Let's see. Do we have any more questions from the people watching? I'll give a couple seconds because we're on a couple second delay, just to give people an opportunity to ask any questions. While we're waiting, are you going to be doing some more audio in the future then, as a hobby?
Who knows? Yeah, I think yeah. I want to figure out filtering stuff and nonlinear effects and like whatnot.
Yeah, amazing. Great. Looks like we're done with questions. Thank you very much, Pavel. And that was really awesome. I will paste the link one more time in the chat, and I will also put this in the video description as well for people to have a play around with. Absolutely essential knowledge for anybody who is trying to learn the fundamentals of digital signal processing and aliasing, oversampling, and things like that. So thank you very much. Thank you very much, Pavel.